Gonna talk about the merits of the Muckpile Block Model with Brice. Brice is a co-founder and CEO of Augment for the last 6 years, and he's been leading a team of AI developers to solve a problem that has, at best, only been mitigated in open-cut mining, ore loss and dilution from blast movement. After spending the initial 4 years developing the solution with First Quantum's copper mines, the last 2 years have been spent traveling a lot around the globe, developing the solution with local gold operations like Northern Star, African PGM operations, and even getting as far north as the Arctic Circle. With the success update of the Muckpile Block Model, today Brice leads a team of 12 people, including 3 amazing geos who implement and support the software. Welcome, Brice.
So thank you everyone for your time. I always love coming to this symposium. It's always so good to see so many different sites doing so many different practices. The wisdom you get from learning how different every individual site can be is really the best way to move forward. I have done this presentation a couple of times. We've been partners with Datamine for over 4 years now, and seeing that I've got a couple of current customers as well as prospective customers in advanced discussions, hopefully a few new customers in the room, I've chosen to do a little bit more of an intermediate dive into why a Muckpile Block Model is so revolutionary for open cut hard rock mines, as well as at the end I've got a sneaky and extra little feature to show off. So just to introduce it, right? So in an open cut mine, where we're starting on the right is with your plan, right? You've got your bench before the blast, and this survey shows you the area. And underneath is your grade control model. That is your understanding of the resource in the best capacity you have. Whereas on the right-hand side, we have this muck pile, which is actually what we want to mine, right? This is what must be marked up. And you generally don't know it that well, right? What the ideal thing to have would be another block model that shows you everything you knew before the blast, but has an estimation of how the blast has changed that material makeup. So whilst we all understand dilution is going to occur, it's inevitable, and we encourage the drill and blast people to do it, consciously or not. But when you look at these two block models, they are the exact same tonnage. Right? No material has been lost or created, and you'd say the same for grade. Whilst it's been diluted, it's still all there somewhere. And the question is it now still recoverable in the same tonnage as I was expecting from the schedule, which hopefully had some way of accommodating for ore loss and dilution due to blasting. But what we're hoping to present geologists with now, with the Muckpile Block Model, is a very precise understanding of how the blast has changed the material makeup, such that your production geology team can make better decisions and truly minimize ore loss and dilution due to blasting. So the basis of our solution is this high resolution surface scan of that post-blast muck pile. And as you can see in this image here, we use that surface scan to actually create a block model. So when we say perfect fit, we are talking about a meter cubic resolution. And so you can see cubic meter blocks dipping above and below that topography. But what this means is that when you go to load something from that muck pile, or better yet, you go to survey or measure something about that fraction material, you have an estimate in every cubic meter of what is there. And this allows not only for amazing validation practices, because this is a full 3D model, every single cubic meter of that muck pile has a block representing it, but it also means that you have this inherent trust in this methodology, because it does flawlessly fit to the surface. Every single cubic meter block you had beforehand exists there somewhere, and the essential underlying part of how we get to that is what I'm going to cover in the next few slides. So this process does use a pre-blast surface as well. And what this does is it's another actual measurement to define the volume we're looking at. So where your blast master may have had a pretty nominal polygon, or, you know, if you were to maybe just look at the drill collars and create a simple surface, you'd get a rough estimate. But as we were talking about, there's always a deviation between plan and actual. And so basing more and more of your decisions and more of your calculations on actual data is one of the things we're proud to bring into you. And you can see this surface scan isn't just about where we were drilling. It's also about this massive space in front that we're about to move material into. So we want to understand the context around this blast so that we accurately track how material is moving into it. So talking to the deviation between plan and actual, right? One of the things this helps with is that we're going to use this surface to slice the grade control model and take a volumetrically accurate representation of what you knew beforehand. So when we talk about the blast master and the intended drilling program, I'm sure we've all experienced that, schedules get bumped up or delayed, and so you don't quite drill the volume you thought you did. And earthworks are also moving material in the region. So you can see this simple colored plot in the right-hand corner is showing the green region, which was indeed what was meant to be blasted, as well as what was designed to be blasted. But then you've got this red region on the corner, which was actually meant to have another couple rows of drilling, but they didn't happen for one reason or another. And so that volume is not being fragmented and will not be part of this shot to be mined. And as well as the blue region is that idea of additional material, which got incorporated there, which you want to have an estimation of, right? You need to know all of this material that's about to be sent to certain stockpile destinations. And so because we're modeling blasting, the drill and blast parameters are very important to us. We take easy exports out of whatever program that you're using to design your drilling and blasting parameters. And particularly, we also are very big on making sure that's quality controlled information. So talking about the same deviation between plan and actual. So we use the floor of these drill collars and the eventual azimuths of anything that you're doing to create a toe surface on the bottom. And whilst, again, in theory, the plan is that that's a perfectly flat bench RL that aligns with your pit, or maybe it's an incline if you've got a dipped resource. But we're using actual data here to create that toe wireframe. Again, making sure we're slicing out of your grade control model exactly the volume that's about to be fragmented. So our system utilizes a completely custom-built physics engine, which I've just got a little graphic playing on the right-hand side here. So you can see each individual cubic meter block freely moves, interacts with other particles, and bounces around. And from the same bird's eye perspective that we've got the physics simulation running, we have an actual video of that actual blast. So whilst the dust definitely hides a little bit of the magic here, you can see that that surface is what is inside our physics engine, where we have an artificial intelligence algorithm fine-tuning variables of the physics engine, as well as estimating some variables too. And this is to counteract the flaw of physics simulation approaches, which is they're too rigid, too deterministic to be reliable, but they also don't have the required accuracy of the input variables you would have to measure to make it accurate and reliable. So AI in this sense has actually learnt an intuition, forgive the personification, but because we've trained it over thousands of blasts, over dozens of different commodities all around the world. And this is what makes our system both intuitive, but also very quick and rapid. So to give you a quick show through of what this kind of looks like, I've got a cross section here of one blast. So starting from the bottom, we've got this blue toe surface. As I mentioned, this is showing you the base of the shot. And whilst it was meant to be the new bench RL, it's kind of wiggling a little bit where the drilling varied in the actual depth it ended up at. We have a grey pre-blast surface, which is constraining all of these vectors that I'll walk you through in just a sec, and the red post-blast surface, all of these being a nice 1 meter cross section to give us a humanly interpretable part of this shot. So constrained between the toe surface and the pre-blast surface is the in situ location of every cubic meter block we're about to simulate the movement for. And I've got on a Euclidean vector here showing the magnitude, the inclination, and the horizontal direction of every single cubic meter that moves. So I've decided to leave on in this cross section where the high-grade ore was. This is a stratified resource, so you can see that nice stratum going along the dip of about 20 degrees at that cubic meter resolution. So you've got your eyes on the prize. This is what we want to know. Where does that end up post-blast? And how much is it diluted, so we can make this trade-off between recovery percentage and maintaining the grade we need for certain destinations. But as I mentioned, this is just 1 cubic meter cross-section on what normally is hundreds of thousands of meters that we're blasting. So in the next slide, I've got this video that's going to now pan through the post-blast volume, showing you that stratified reef and how we have modeled every single cubic meter of it lifting up. So the waste and everything below the cutoff grade is filtered out. We're just looking at the actual high grade ore. But you can see as we move towards the west end of this blast, you can see the topography moving back and forth. And this is not uniform, right? Each individual cubic or 1 meter cross section has changed completely differently from one end of the blast to another. And so I'm really illustrating here what we mean when we say resolution, right? The high resolution to model what has actually happened to your ore. So one really interesting part of our method that we have used is this idea of air blocks. And we call them air blocks to be cute because they're actually absent. They don't exist. There is no centroid or UID. But the idea of our method is that we don't want to change any of your estimations from your grade control model. And that's how we can achieve a flawless balance of tons and grade down to whatever significant figure you use. So when we do our relocation estimation, we're constraining blocks to a regular and orthogonal grid. And that's what makes it a true block model that can be imported into any geological modeling program and even mining software if that's the way you'd like to use it. But part of our relocation estimation is strategically blocking these air blocks such that when we talk about what material ended up in the highest part of the heave, the furthest part of the toe, we've got this perfect conservation of mass by limiting the volume it can move into. So an easy way to think about this is if you start with 100,000 cubic meters, you might end up post-blast with 120,000 cubic meters, even though it's the same tonnage. And so in this scenario, we would have put in 20,000 air blocks to accurately represent where the density has dropped because the material is now fragmented without actually changing your density variable at all. So because we have this perfect fit to the post-blast surface and essentially what is sitting in your pit waiting to be mined, it actually facilitates validation of our model really well because it means you can go to any part of this surface, or if it's been mined, any part of the muck pile, take a measurement, a sample, right? And then create a validation method. So if you're lucky enough with your ore body to have visual markers, then there are some pretty easy wins you can have. And in this video, what I can show you is that that same stratified reef that I demonstrated in the previous example, we can filter away the waste blocks in the same manner such that when the mining team actually expose the reef, they can take a top of reef contact survey, which is a true 3D point, and we can load in the true 3D points from survey as to where they found the contact point of the reef. And with that, you can then search for the nearest cubic meter block to those samples and create a difference and error sample between the top of the reef that was observed versus our estimated top of reef contact. And when we've done that in quite a few studies with the existing customers, we're finding that we do have an average error of 1 meter, which for a cubic meter scale is about as much as you can ask of us for our estimation process. So then you can take our block model and now apply these mining factors. So here we're wrapping this reef in an implicit ISO shell inside Studio RM, and then it just goes downstream to the mining team like it normally would. It's the same old dig plan analysis you would have always done. So because our method is a really advanced physics engine, we're able to simulate all of the niche and edge cases that we see in open cut mining, not just your routine free face moving forward or center lift lifting up. And I've got a quick example here of a choked blast. So you can see in the diagram on the left hand where I've taken this cross section to make sure we can focus on an easy to understand segment of the blast. And this material is all moving towards that top left-hand corner where there's previously mined material blocking it. So again, that's shown really nicely in this cross-section here with the grey pre-blast surface showing you where everything was before the blast. And I've loaded on that portion of the grade control model to show you what's actually being fragmented and needs to be estimated how it'll move. So because of the legend scale from this gold example, you can see the material right up against the front of that buffer is all high grade. And the pink part is even higher grade that really emphasizes how precious it is and how much we need to track its movement. So when the shot goes off, our physics simulation takes all of these estimates where you can see the choked material at the front really is lifting up and moving around, whilst when you get further to the back of the shot where the burden and relief pattern steadies out, you get a lot more consistent and nominal movement. And the larger arrows there are actually blast movement monitors, which where customers have, we highly encourage those measured vectors as one way to provide evidence of especially movement lower down in the shot. So the final result of these vectors leaves you with this. So this Muckpile block model is showing you how that material has now cast up and over the blockade and left you with a really good way of estimating the dilution that's occurred to make sure you don't leave behind any of your high grade material and accommodate for these niche scenarios that do happen, right? We wouldn't have planned to have blasted this shot, but we need to work with the realities that we experience from day to day in mining. So again, talking about realities, and another niche application of our really advanced physics engine is that some of the larger open cut mines we're seeing in the current economic paradigm have previous underground workings. And these underground workings represent a large volume, particularly with some stopes that we see in gold mines, that material is going to fall into. And whether it's got grade or not, that cavity and the way it's going to change material flow changes the location of all of the material in that blast. So this diagram is showing you a really nice underground volume that was part of this shot. And you can notice in the topography of the surface of that post-blast environment that very obviously it was heaving up and then it's just crashed down where things have absolutely fallen below the bench. And so we're able to give you not only an accurate estimate of that kind of movement, but you can append this block model to your grade control practices such that when you eventually get down to that bench where that underground working is, you've got an accurate estimate of what's there. And this helps mines adapt to all the kinds of things they experience day to day. But one of my more favorite examples of this advanced functionality is rilling down a pit. So this example is actually showing you where material has fallen over 60 meters down through 4 benches, and it actually had to happen consistently. This is in a larger pit where decisions were made decades ago that kind of forced this to happen. It's really not ideal. No one would have planned for this, but nonetheless, you can see in the 3 plots at the bottom, each subsequent blast we're able to re-simulate how rilled material now rills again and rills for a third time to populate an accurate estimate of rill cones that are forming at the bottom of this pit. And when the time comes to come and actually mine this material, rather than thinking of it as sheeting and spreading it all over the haul road, you can actually prove to your team that if you were to mine this in a way where it rills down on top of you and you're able to only mine in a vertical segment, which parts of this are actually above the high grade threshold or marginal grade thresholds. And this essentially represented millions of dollars for this operation. And we have a really good quote from that geologist who I wasn't able to get approval to put a branded logo behind in time for this Symposium, but hopefully that'll come out in the near-term future with a beautiful logo next to it. So, whilst the Muckpile Block Model is amazing information, I also wanted to take a moment to talk about our integration with Ore Controller. We had a really good presentation from North Parks earlier this morning on why Ore Controller brings that level of consistency and the automated reporting to grade control practices. So with the Muckpile Block Model, all of this reporting now essentially has a whole new category of plan versus actuals. And especially if you've completed your material type delineation, you can get those automated results about ore loss and dilution on a blast by blast basis. So Augment has worked with Datamine to embed our workflow inside Ore Controller. So you don't have to leave Ore Controller, and when you configure the Ore Controller workflow, you will look at the pre and post blast surface, import that data, and get a Muckpile Block Model all as part of the standard operating procedure. And this means that now you have this new level of precision to look at precision mining techniques. So when we talk about cutting multiple flitches, you know that you're able to accurately know where material has heaved up into that flitch or fallen down into a different flitch. And you can delineate that in a way that works with your fleet equipment, right? If there's a particular dig angle that you're forced to dig at, then the Muckpile Block Model is composited at that dig angle such that you can see the difference between mining perpendicular to strike or taking it however you feel, right? And the tonnage and grade differences between those approaches are reports that you probably want to see, right? Especially when you incorporate fleet management data as to what was actually loaded versus what the plan was to load. So the beauty of Ore Controller has this really easy to read table in that left-hand corner that will show you the average grade and tonnage of every single material type delineation you've made. And when you see that the average grade is higher than it really should be, you can quickly expand that delineation to incorporate more marginal grade material and maximize the tonnage of your high grade ore. Where obviously the opposite is also true. If you find it's a little bit below spec, then you tighten the delineation and make sure you're delivering the right spec of material, which only becomes more relevant when we start to talk about sites that have multiple different attributes to delineate their material types. So if you've got a sulfur grade to watch, right? Sulfur is displayed right there with all of this. And it's dropped off that last slide. And the last bit that's worth talking about is this really nice Sankey plot. So the Sankey plot, again, talking about the difference between plan and actual, is showing you on the left what was scheduled, right? The scheduled delineations of what you thought was going to be your high grade, medium grade, and waste. And then you can look in the post blast, once you've finished your mark out, where that material actually got diluted together and mixed and has now formed your post-blast material type delineations. And so it's really insightful for you to see the real effects of ore loss and dilution due to blasting in this one Sankey plot. So with the Muckpile Block Model covered and our Ore Controller integration shown, I did want to show off a new feature that we are actually putting into beta testing with one client this month. And it is our dig plan optimizer algorithm. So when we've gone to our customers and asked them for feedback and talked to them about what parts they don't like about our process, the most common feedback we get is that geologists now have to delineate these material types under time pressure, right? Which can be stressful. Mining engineers have a habit of hovering. And so it eventually means that you don't do as many iterations of maximizing that grade and tonnage that you could have without the time pressure. So our dig plan optimizer algorithm is not too different from a mining stope optimizer or some other scheduling algorithms, but we've made this explicitly to work on the Muckpile Block Model. It's working on our high resolution scale as well as your selective mining unit, and is specialized to rapidly cluster all of your ore and produce what we're trying to pitch as a really good starting point, but we're not going to be surprised if people call it an easy button for creating rapid delineations. So the way that we're currently exploring this is we think the actual constraint to look at is how do you define a mineable shape? Because the mineable shape needs to take into account a minimum tonnage of what your haul trucks are, a minimum width of what your loading bucket size is. And if you're going to be flitching, we want to divide the Muckpile Block Model out into each individual flitch and do them separately. So once we've defined mining constraints, it's really easy to talk about geological definitions. We're just taking all of your grade attributes, the grade bins that define them, and we even use your exact legends and color scales to make sure that it's as you would expect to analyze it. So I'd really love to engage the audience and get some questions about this mining definition, because that is our core hypothesis right now of what we're beta testing with this client, is how do we define a mineable shape, right? It's actually a lot harder than we thought it would be, and why we've let this process be manual for so long. But assuming that we do have a good definition of a mineable shape, from here, it's essentially a tonnage maximizing algorithm. So our clustering process is based on an exploration process where we've taken inspiration from image analysis AI algorithms to use a method that is exploratory. So it will incorporate too much waste material and then bring it back to make sure it truly can find the largest cluster. But from there, it's just going to create all of your highest grade clusters in the order of precedence, and then move through and do your medium grade, low grade, and even delineate your waste for you. So the automated process of this, as I mentioned, ideally is just an advanced starting point for a geologist to then come and impart their intuition, adjust the final result. But the reporting that comes out of this is the other beauty of it, right? Is that very quickly you've been given all of these results about what the average grade and tonnage could be. And once it's finished, we're currently automating some reporting. And you can see, again, this is why the connection with Ore Controller is so amazing, is any of these reports that you've already configured in your workflow, we've now got an algorithm that's going to delineate these material types and jump you straight to analyzing the result before you come back and fine tune it, before you push it to your senior or super to get it approved. So I think there, I'd really love to engage the audience if I can get some questions and to try and provoke the right kind of thinking. I would love to ask, if we do have a good algorithm for automating delineation on a block model that understands how the blast has diluted your ore, is the geologist the right person to be creating a dig plan, understanding the mining assets and equipment? And the flip side of that is, if you were to consider a mining engineer creating that dig plan, are they able to delineate material types and interpret these models in a way that, if the information's there, can the knowledge be imparted? And the balance between those two things, I find, is normally good thought-provoking content to get people's opinions on the table. So I'll leave the presentation just with one final note, that if we have truly made the best ore delineations possible, that the next biggest source of ore loss and dilution is precision mining. And we need to look now to overmining and undermining and compliance to these dig plans to truly increase the amount of ore to the mill.